Alright, so this video is going to be the beginning to our section 3.7 notes. 3.7 is about what we call implicit differentiation. Before we get into implicit differentiation though, I want to just review a few things with you. First of all, I have on the board two examples of the chain rule. This will be important for us because in implicit differentiation, it's really just an extension to the chain rule. If you haven't done your chain rule homework yet, I would suggest that you go ahead and do that 3.6 homework before going through this lesson, because the more you understand the chain rule, the better off you'll be with implicit differentiation. Okay. With that being said, I have two examples of the chain rule here on the board. The first one is kind of an extension of the power rule. You've got the derivative of some function raised to the 7th power. So we do our power rule, 7 times that function raised to the 6th power. But then to finish the chain rule, you multiply it by the derivative of whatever that inside function was. In this case, the derivative of log base 5 of x is 1 over x natural log 5. Okay, so we finish it off by multiplying by the derivative of the inside. The second example, again, we have an outside function sine and an inside function x cubed plus 4x squared. According to the chain rule, if I want to do the derivative of this function, I'll start by doing the derivative of sine, which we know is cosine, and we leave the inside alone. We don't touch it, we leave it like it is, x cubed plus 4x squared. And then what the chain rule says to do to finish the derivative is you multiply by the derivative of the inside. The derivative of x cubed plus 4x squared is exactly what we have written here, 3x squared plus 8x. Okay, so the idea of implicit differentiation is we want to imagine that these inside functions that we're working with are functions that we don't know. So let's take these same two examples and suppose I don't tell you what those inside functions are. Alright, so let's take this log base 5 of x and let's pretend like that's just some function that I don't tell you. We can just call it f of x if you like. So if I don't tell you what that function is, then to do the derivative of this thing, the derivative of some function that I'm not telling you to the 7th power is going to be, according to the chain rule, 7 times, leave that inside function alone, to the 6th power, and then multiply by the derivative of that inside function. Okay, so this is just the chain rule. What we'll be doing with implicit differentiation is instead of having this inside function, instead of calling it f of x, usually we'll call it just y. So let me do this one more time. Suppose I ask you to do the derivative of y to the 7th power, where again, that y represents some function of x that I'm not telling you. Okay? Since that's some function of x, I have to do this derivative with respect to x using the chain rule. I have my outside function, I have something raised to the 7th power. According to the chain rule, the derivative is you do the derivative of the outside, 7 times something to the 6th power, but that inside you just leave alone. You don't do anything to it. But then to finish the derivative, just like we did over here with the f prime of x for the chain rule, I have to finish by multiplying by the derivative of the inside. The derivative of the inside in this case, we usually write it as dy dx. Okay, but you could technically also write this as y prime. Y prime and dy dx mean the same thing. In this second example, again, take this inside function and pretend like I didn't tell you what that inside function was. We'll just call it y. So if I want to do the derivative of sine of y, where y is some function of x, then I know that the derivative of my outside function is cosine, so I have cosine, and I leave the inside alone, cosine of y. But then to finish my derivative, I multiply by the derivative of the inside, so that's the derivative of whatever that inside function is. So that would be your y prime. Alright, so this concept of the chain rule where we just don't tell you what the inside function is going to be important for us in implicit differentiation. The next thing I want to show you as kind of a preview or something to kind of get you ready for implicit differentiation is the idea that when we have equations, we're used to seeing equations written explicitly. Okay, so for example, these functions over here, I have these three functions are written explicitly, where y is written in terms of x. So in other words, I have a y on the left-hand side, and all I have on the right-hand side are terms involving x. Okay, so we say that y is written explicitly in terms of x in all three of these cases. This is an example of explicit expressions. Okay, when we do implicit differentiation, we're dealing with something a little bit different. We're going to be dealing with implicit equations. So what we have on the right-hand side here, we no longer have y being explicitly written in terms of x like we did over here on the left, where we had y all by itself on one side and then just x's on the right-hand side. An implicit equation is some equation that gives you some kind of relationship between x's and y's, but it's not written explicitly. In other words, it's not written in the format that we have over here on the left. So these three equations here are examples of implicit equations. Each one of them shows us some relationship between x and y values, but none of them are written explicitly. One thing I want you to understand, which will get back to the idea of implicit differentiation and the applications of what we'll be doing in this section, is that when we have these implicit equations over here on the right, we can graph most of these things just like we graph functions like these ones on the left. Okay, in other words, there are points x comma y that satisfy these equations, and if we plot these points, we could figure out what the graph looks like. Now, this lesson isn't a lesson on graphing implicit equations. I don't need you to worry about how to graph these things. I just want to show you an example of what a graph might look like. Alright, so let's take this first equation here, and let me show you what the graph of that equation looks like. It's going to be one that you've never seen before, probably. So if I graph x cubed plus y cubed equals 6xy, you get this weird loop here shown in blue. Okay, again, this is probably not what you'd expect from graphing something like this. You've probably never seen a graph of an implicit equation. But the bottom line is, every single point along this blue line is a point that satisfies that equation. For example, this point right here on the end of the loop is the point 3, 3. We could verify that 3, 3 satisfies this equation, because if I plug it into this implicit equation, both sides come out to be the same. If I put in 3 for x, okay, so here I've got an x value and a y value. If I put in 3 for x, I have 3 cubed, and I put in 3 for y, I have 3 cubed plus 3 cubed equals 6 times 3 times 3. And after some simplifying, you get that both sides come out to be the same. They both come out to be 54. So, in other words, this point, 3, 3, is a point that works in this equation. So that point, 3, 3, is a point on the graph of this equation. And you could try that again an easy one to check here, you can see that this graph passes through the point 0, 0. And it's fairly easy to see that if I plug in 0 for x and 0 for y, everything works out. Because in this case, it's just 0 equals 0, everything's fine, both sides come out to be the same, so the point 0, 0 is a point on the graph. Okay, so I show you this just to kind of get across the idea that even though this isn't a lesson on graphing implicit equations, a lot of these implicit equations that we'll be working with do have graphs, and if they have graphs, then we can talk about one of the main applications of derivatives, and that's tangent lines. So for example, if I wanted to draw a tangent line at this point 3, 3, it would be a line that comes in and just touches the graph at that one point. If I want to know the equation of this line, then we kind of already know how this works. If I use point slope form, I have y minus my y value equals the slope times x minus my x value. We've done this before. Now the only thing we're missing is the slope of this line. And just like what we've done before, the derivative tells us how to find the slope of any tangent line on this graph. So your next lesson on implicit differentiation will tell you exactly how to find the derivative of y with respect to x for this equation. If we can find the derivative, then we can fill in the slope of the line. Alright, so this is going to be one of your main applications to what you see in the next video.